Welcome back to Calculus 2. I'm Dr. Jeff Grove. Today we're going to talk about physical applications. To begin with, I'd like to talk about mass, and in particular, suppose that we have mass that is distributed with a variable density. Density is often denoted by the lowercase Greek letter rho. Rho is written like this. The uppercase rho is this. This is not what we're doing. This is spelled R-H-O, rho. Sometimes, when I'm solving a crossword puzzle posted in a newspaper, the clue will be symbol for density, and the answer will be rho, R-H-O. That just goes to show how common the knowledge is that density is represented by the Greek letter rho. What we're dealing with in a situation like this is a linear density. You're probably most accustomed to dealing with a volume density. A linear density has units of, say, kilograms per meter, as opposed to a volume density, which has units of kilograms per cubic meter, or an area density, which has units of kilograms per square meter. Here we have a linear density, which will be a function of a single variable, x. To get the total mass, at some x coordinate, we'll make a little slice of width dx, some infinitesimal slice. The element of mass denoted by dm is the density times the little interval dx. Think about the units. The units are going to be kilograms per meter times the units of dx, and dx does have units. It's a little increment in length. It will have units of meters. We'll get a little tiny element of mass, a little element in terms of kilograms. To get the total mass, let's say between A and B, what you do is you add those up from A to B, rho of x dx. That gives you the total mass. We're trying to teach you a new way of thinking about integrals. For example, let's suppose that the density is given by 2 times the sine of x, where x takes values between 0 and pi. In other words, we're dealing with a kind of mound of mass going up to 2 units here. Find the total mass. The total mass will be the integral from 0 to pi times the 2 sine of x dx. The 2 can come out of the integral, and then we're just getting the area of one bump. Remember, one bump gives you 2. The answer is 4, whatever units of mass you happen to be dealing with at the moment, perhaps kilograms. If I want to find the center of mass, consider a distribution of mass. And let's suppose there's a fulcrum, kind of a balancing point. This goes from A to B, let's say, and we have a balance point, x bar. If you take a thin slice of width dx at some point x, then the amount of mass right there, the little element of mass, is rho of x dx, assuming that the distribution of mass is given by a mass density rho of x. That's your little element of mass applied right here. At that value of x, there's a lever arm length. There's a moment. As you know from your experience using wrenches, the longer that lever arm, the easier it is to turn. That's called the moment. So the moment will be, the little element of moment is going to be the lever arm length, which will be x bar minus x, times the element of mass, rho of x dx. If x bar really is at the balance point, then the moments on the left-hand side, which will be positive by design here, will cancel the moments on the other side. Since x is bigger than x bar on the right, we will have negative values for that lever arm, which will give you moments going the other way. The moments going one way should cancel the moments going the other way if x bar is placed at exactly the right point, the balance point, the center of mass. This means that if we add up those moments, we should get 0. It should perfectly balance. The total moment is 0 if x bar is placed just so. Let's see what the implications are here. We can separate this into two integrals. The integral from a to b, x bar is a constant, and it can come out of the integrals. We'll have rho of x dx, minus the integral from a to b of x rho of x dx. The second integral represents the moment about the origin, about x bar equals 0, if you will. The moment about the origin. The first integral is the total mass. The nice thing about this equation is that we can solve for x bar. We can figure out where that center of mass is. All you have to do is move this to the other side and then divide the other factor off to solve for x bar. Here's what you get. We have x bar is the integral from a to b of x rho of x dx divided by the integral from a to b of rho of x dx. That's the total moment divided by the total mass. These are pretty easy to calculate. Let's do an example. In our last example, we had a mass distribution of the form 2 times the sine of x, where x was between 0 and pi. A nice big bump of mass like this. It's pretty obvious that the center of mass should be at pi over 2 due to symmetry here. Let's verify that our formula gives us exactly that. The center of mass is the integral from 0 to pi of 2x sine x dx divided by the integral from 0 to pi of 2 sine x dx. We already know the value in the denominator is 4. 2 times 1 bump. 1 bump gives you 2. 2 times 2 is 4. So the denominator is 4. To get the value in the numerator will take a little more work. I'll have to show you that an antiderivative of x sine x. Here's my claim. If f of x is x sine x, then an antiderivative will be sine x minus x cosine x. We can prove this by just calculating the derivative. I'll have to teach you later how I figured this out. The derivative of sine is cosine. I'll write that as a c. On the second term, I need to use the product rule. Derivative of the first is 1 times negative cosine. And then I get the derivative of the second. The derivative of cosine is negative sine. Negative negative gives me positive, and I'll have plus x sine x. That proves that sine x minus x cosine x is an antiderivative of x sine x. That allows us to calculate the integral using the fundamental theorem of calculus. So far we have this 2 divided by 4 gives us 1/2. The antiderivative was sine x minus x cosine x, and we're evaluating from 0 to pi. The sine at pi and the sine at 0 are both 0. So this term contributes nothing to the answer. Everything will come from the second term. We'll have 1/2 times. We have the cosine of pi. The cosine of pi is -1. So we'll get negative, that's positive, pi. And then when we plug in 0, we get 0 times cosine of 0. That's 0. So the answer is pi over 2, just as we advertised. So the formula is giving us exactly what we expect. It does illustrate an important problem. We need some efficient tools for calculating these antiderivatives. That's what the entire next exam is about. Don't worry, we'll teach you how to do this. Next, I'd like to teach you about work. If I push down on this table and the table doesn't move, I've done no work. It has to move to do work. You have to have a force and you have to have a displacement. If the force is exactly in the direction of the displacement, then the amount of work is force times displacement. But what if the force is variable? What if the force depends upon the displacement, much like it does with this mass on a spring? In this case, there's something called Hooke's law. If you stretch the spring some distance x from its equilibrium position, then the force, which will be a function of x, will be proportional to the displacement. That's Hooke's law. Note that the force will be variable, so the work done in pulling this will also require a deeper analysis than just this. This won't be good enough because the force will be a function of how far you've stretched the spring. In our spring example, let's suppose that we've stretched the spring out to here, but at some point x, we want to calculate the little tiny element of work that is done in displacing the mass some very small amount. In that case, the little element of work is the force at that displacement times that little infinitesimal displacement. We'll assume that from x to x plus dx, where dx is very tiny, the force is approximately the same all the way across, f of x. In that case, the total work will be the integral from a to b of f of x dx. That allows the force to be variable, which it is in quite a few circumstances. A force of 10 newtons is required to stretch a spring, let's say 0.1 meters. How much work is done in stretching the spring from equilibrium to 0.4 meters. The work then will be the integral from 0 to 0.4, and then we need the force. The force is going to follow Hooke's law. The problem here is, at the very beginning of the problem, we are not given the spring constant. Hooke's law says the force is k times x, but what is k? That's where this first little bit of information comes in. 10 newtons is required to stretch the spring 0.1 meters. So k is going to be 100 newtons per meter. So we are going to have 100x dx as the integrand. Integrating, we have 50x squared evaluated from 0 to 0.4. That's 50 times 0.4 squared minus 0, of course, or 50 times 0.16. Remember, 50 is 100 divided by 2. And if we multiply 100 times 0.16, we get 16. Divided by 2, we get 8 Newton meters. Hopefully these units will make sense. Remember, 100 was in the units of newtons per meter. We're multiplying it by meters, and then multiplying it by meters again, giving us Newton meters, also known as joules. In our next example, we're going to have a tank, let's say on stilts, and we're going to pump water, or at least a fluid with a constant density of 1,000 kilograms per cubic meter. And we're going to fill up this tank. Let's suppose the tank has a radius of 1 meter and a height of 2 meters. How much work is required to fill the tank? The idea is kind of like this. If we're going to fill the tank, we're going to have to transport little layers of water up. Let's also to this level. Let's suppose the height of the tower is, let's say, 10 meters. That layer has to go up 10 meters and then up to its position above. Let's suppose that the coordinate system that we apply has y values here from the bottom of the tank to this layer. So we're going to have to transport that layer of mass from ground level to 10 plus y meters. How much mass is in that little thin slice? Using the theorem of Pappus, it should be the area of the face times a little thin slice of dy, that amount that you slide that to find the volume. So the little element of mass will be the density, which is in kilograms per cubic meter, times that little element of volume. That's the density times pi r squared times that little element dy. The little element of mass is pi rho dy. That mass times acceleration due to gravity gives you the force. So the little element of force is the acceleration due to gravity times the element of mass, mass times acceleration. That's going to give you pi rho g dy as the little element of force. To calculate the little element of work, we take the element of force and multiply by the distance, 10 plus y. Our little element of work is pi rho g times 10 plus y dy. That means the total work done. Well, the integral, remember the y values went from 0 to 2. It was a tank 2 meters tall. Pi rho g times 10 plus y dy. From here, it's a simple matter of calculating a very simple integral. We obtain pi rho g 10y plus y squared over 2 evaluated from 0 to 2. That's pi rho g times 20 plus 2 squared is 4 divided by 2 is 2, and of course minus 0, or 22 pi rho g. Let's use 9.8 for g, and rho is 1,000. That gives us then, according to my calculator and rounding to two significant figures, 680,000 and the units will be Newton meters or joules. Next, I want to talk about hydraulic force. For anyone who's been swimming deep into the lower depths of a swimming pool, you'll know that the pressure on your ears increases the deeper you go. So pressure, which is measured in force per unit area, let's say units of newtons per meter square, will depend upon how deep you go. Suppose you have a fluid and you have a certain depth y. What is the pressure at that particular depth? It also depends upon the density of the fluid and, of course, the acceleration due to gravity. So it's going to be rho g y. Rho, the density, g, acceleration due to gravity, and y, the depth. Let's calculate the units. So what you have here is kilograms per cubic meter times the acceleration, which is given in meters per second squared. Notice kilograms times meters per second squared are newtons. And we're multiplying that times meters. We'll cancel 1 meter off and get newtons per square meter. Let's suppose that we have a trapezoidal-shaped dam. At the bottom, let's suppose that it's 20 meters wide, and at the top, 30 meters. The total depth is, let's say, 15 meters. I want to know how much force is on the dam. Here's what we'll do. We'll take a little thin cross section where at some depth, y, the force at that depth will be more or less a constant. It'll be the pressure times the area of that very thin slice of width, dy, of course. To figure out the area, though, that will depend upon where we take the cross section. At a depth of 15 meters, that little area will be dy times 20 meters. It's 20 meters wide, dy meters thick. But at other depths, we'll get a little bit more area. So what we'll do is we'll define this little value over here to be x. So the width will be 20 plus 2x. So the area will be 20 plus 2x times dy. But x will depend upon y. How does x depend upon the depth? Well, what we'll do is we'll use similar triangles. X divided by 15 minus y will be equal to, we'll split the difference, 5 meters and 5 meters on each side here with 20 meters between. 5 divided by the entire depth of 15. We can solve for x by multiplying by 15 minus y onto both sides. We reduce the fraction to 1/3 and distribute. We'll obtain x equals 5 minus 1/3 y. Our little element of area will be 20 plus 2x, and x is 5 minus 1/3 y, times dy, the little thin slice, height of the slice. Distributing, we'll have 10 plus 20 is 30, minus 2/3 y, all times dy. That's our element of area. And remember, area times pressure is the force. Our little element of force is then going to be pressure times the element of area. It's going to be rho g y times 30 minus 2/3 y dy. This gives us rho g times 30y minus 2/3 y squared dy. To calculate the total force then, we add up the elements of force as y tends from 0 to 15. We have then rho g times 15y squared minus 2/9 y cubed evaluated from 0 to 15. What does that give you? My calculator is giving me about 26 million newtons of force, using the values 1013 for the density, 9.8 for that's the limiting factor in terms of the number of significant figures. For the acceleration due to gravity, I guess we could have used 9.81. And then plugging in about 26 million newtons. This method for calculating the fluid force on a dam was first invented by a Flemish engineer, Simon Steven, who died in 1620, long before Sir Isaac Newton was born. You see, he used methods similar to our taking of limits, but not quite at the level of finding integrals, definite integrals by limits of Riemann sums, and certainly nowhere close to the fundamental theorem of calculus. So he was anticipating, long before Sir Isaac Newton was born, the methods that would become important in integral calculus. So to recap, if you have some strangely shaped dam, you'll have an element of area that will depend upon how deep you are. The element of force will be rho g y, that's the pressure, times the element of area, which will depend upon y. The total force then will be the integral from a to b, of rho g y times that element of area, which will be a function of y. That element of area will depend from problem to problem. If you're dealing with a submarine window, the element of area will depend upon where you are on the cross-section of that window. So we can't determine what this is until you state what the problem is.